All right, y equals x. That's probably good enough. Let's pull some of these up and just get an idea of what some of them look like. So if we focus just on y equals x squared, we get a graph that looks something like that. So we'll copying down. Goes through the origin, curves up in either direction. Y equals x cubed. While positive number, maybe qualitatively, that looks kind of similar. Except close to the origin, it doesn't grow as quickly. Once it gets past x equals 1, it grows faster than x squared. And for negative numbers, the result is negative. Y equals x to the 4th. Let's pull it up along with y equals x squared. How would you say those two functions compare? What are some words you could use to describe similarities or differences? Well, they both kind of have the same rough, bowl-ish shape, right? Maybe the one to the 4th that looks a little bit more squared off close to the origin. Its edges get steeper faster. Here's y equals x to the 4th. Maybe let's put the remaining ones down. So, let's just think about this for a second. Let's classify these, but just by looking at the graphs. Are these even or odd functions? Y equals x, even or odd or not odd? Or both? Odd. It's symmetrical over the origin. X cubed. Even odd, not all. Odd. If you take a point on this graph and reflect it over the origin, you get a new point on the graph. And in fact, let's take a look. Is the same true for x to the 5th? Yeah, same with x to the 7th, x to the 9th. In fact, in this column, you can put anything that looks like x to the odd power. How about the even powers of x? Would you call those even functions or odd functions, or neither? Even, they look like. Right? They're symmetric over the y-axis. These are all even, and in fact, the same will be true for anything that looks like x to the even power. Let's talk about the intercepts of these things. Where are the x/y intercepts of these graphs? Well, just remember, the x-intercept is where the graph crosses the x-axis. Where do these graphs cross the x-axis? At 0, at the origin, 0, 0. And that's the same no matter which you look at. Is the same true for the y-intercepts? Yeah, I think so. Let's grab this. All right, so another set of words we know are words increasing and decreasing. So let's look at the odd power functions, x cubed, x to the 5th, x to the 7th. Where are those functions increasing? Yeah. Okay. Well, let's just see. There's x to the 3rd power. If you look over this interval, and you have x values going left to right, do the y values keep going up? Is there any interval over which they don't keep going up? No. So this function is, I guess decreasing never, increasing over all of the real numbers. Cool. How about the even power functions? Where are they decreasing? For negative numbers. And because of a technicality, I want to include all the way to 0. And let's just think about why. Even if you include 0, as long as the x values keep going left to right, do the y values keep going down? Yeah, they only start going up once you hit positive numbers. Where are the even power functions increasing? I guess it should be like everywhere else, right? From 0 to infinity. Neato. Yeah.
What are odd functions for increasing infinity?
Yeah, absolutely. Another way of saying it overall of the real numbers is negative infinity to infinity. Oh, and I guess I'm using a notation here I haven't described before. The symbol blackboard bold R is often used by mathematicians to indicate all of the real numbers. Mathematicians want to talk about the real numbers often enough, and they don't want to write the real numbers every time, so that symbol just means the real numbers. Any questions right now? All right. So, we can say something qualitative about the graphs of all of these functions. So let's just pull up the graphs of all of the even power functions. X squared, x to the 4th, x to the 6th, x to the 8th, x to the 10, that's probably enough. Can you say anything about the shapes of these graphs? Are they similar in some way? Yeah. They're all roughly bowl-shaped. They open upward. Qualitatively, all of the functions of the form x to the even look similar to y equals x squared. And I'm putting this in quotes because there are differences. X to the 4th is different from x squared, but it looks qualitatively similar. It opens upward in a left bowl shape. Same thing with all of the odd power functions. Anything of the form x to the odd looks similar to x cubed. People feel pretty good? All right, so there's the first of this pool of elementary functions to think of. If you're ever asked to know what the graph of y equals x to a power looks like, you know what it looks like. If x is even, it's an upward opening bowl shape. If x is odd, then it's an upward opening bowl shape for positive numbers, downward opening for negatives. Feel pretty okay? Excellent. The next set of functions that I think I want to talk about the graph of by hand are things that look like y equals x squared. Nope, the square root of x. And think about the graph. I think this is a good time to introduce some of the ideas of inverse functions. So, if you have the equation y equals the square root of x, what would you get if you solved that equation for x? Yeah. Something like that? and I'm going to put a blank here because there's going to be another detail I add. So this sure looks like what you would get if you were to take y equals x squared and the flip the roles of x and y. So that would give you, I guess, something like y equals x squared, but on its side. So there's the graph of x equals y squared. If I wanted that to be the graph of the square root function, something's wrong. Is that the graph of a function? No. Fails the vertical line test. So there's one added condition. So this y value is supposed to be the square root of x. Is the square root of a number ever allowed to be negative? No. So you add one more condition here, and y bigger than or equal to 0. So I'm only going to take the portion of that graph which contains y values that are positive or 0. There's the graph of y equals the square root of x. And there's even how you come up with it. If you don't want to remember what the graph of the square root of x looks like, you just need to remember what the graph of y equals x squared looks like. And then remember that you only care about the positive portion of it. Feel pretty good? Nice. All right, do you think we could do something similar for the cube root function? I think. If you were to take y equals the cube root of x and solve that for x, what would you get x equal to? Or you could just like cube both sides, right? Let's do that. So you get x equal to y cubed if you took that and solved it for x. Oh, nice. I know what the graph of y equals x cubed looks like. Like something like that. Pull out the previous page. If I want the graph of the cube root function, that means I want the graph of x equals y cubed. So I should take exactly this graph, but flip the role of x and y. So this point here at 0, 0 will stay put. These points here at 1, 1 and negative 1, negative 1 will go to the same places. And then instead of carving up steeply, it'll flatten out. All right. Is that the graph of a function? Does it pass the vertical line test? Nice. There's the graph of y equals the cube root of x. Do you think you could do something similar to sketch the graph of the fourth root function and fifth root function? In fact, I think I'm going to pause and let you do that. I'm going to take attendance because I failed to be so the past couple days. Such a one. Alexis Tao. David Bullen. Sam O. Emma R. Nope. Leah. Excellent. Sage. Excellent. Abby. CJ. Excellent. Adrian Rajar. Mason emailed me. Luke Wanars. Excellent. Sam Pishar. Lauren Garbish. Cool. Olivia Robb. Cool. Dayanara, I see you. Jane Wisgard. Excellent. Izzy Wizzo, Ray Gilkinson, Grace Heinen, Emily D, Lauren E, excellent, excellent. Jenny Pinley, nope. Mackenzie, Malcolm, Ellie Mayak, Aries going, Louis Novak. Alright, cool. So, hopefully that one's pretty okay. So tell me, how do you get the graph of y equals the fourth root of x? Should I talk through getting the graph? Everyone's being very quiet. I should. Let's see. So, y equals the fourth root of x. I'll follow the same procedure as before. Does that look like something you could solve for x? Yeah, what would you get if you did? X equals y to the fourth. And that looks almost like one of the elementary functions on the previous page. It looks almost like y equals x to the fourth, but the x and y's are switched. So if you remember that y equals x to the fourth looks something like that, then you can get the graph of x equals y to the fourth by taking exactly this graph, but switching the roles of x and y values. Do this in pink. There's the graph of x equals y to the fourth. Is that the graph of the function? No. So, the thing you have to remember is when you take the fourth root, are you ever allowed to give a negative number as an output? No, fourth root of a number has to be positive. So, we'll take only the positive branch. If you take this, then you get the graph of y equals the fourth root of x. That feel pretty okay? All right. Tell me how you get the graph of the fifth root of x. So it's going to be the same sort of model. You take the graph of one of the functions on the previous page and you flip the role of x and y and see what happens. Y to the fifth equals x. You have the graph of y to the fifth equals x. That looks something like this. That passed the vertical line test? Yeah. So this is also the same as the graph of at y equals the fifth root of x. Neato. So, in general, it sure looks like anything that looks like, let's skip this. If you take an odd root of x, those graphs will all just look like odd power functions but flipped on their side. If you take an even number and take the even root of x, it'll want to look like an even power function flipped on its side, but it won't pass the vertical line test, so you only take the positive branch of it. And let's just take a look at that. This function, even or odd or not odd. And all right, one of the checks is pin down the origin, rotate 180 degrees. Is that the same function again? Excellent. All right, so let's break these into branches. Y equals odd root of x, so like cube root, fifth root, seventh root. These functions sure seem to be odd. Let's compute some intercepts. Where are the intercepts of the odd power functions? Where do they cross the x-axis?
The origin.
Origin. Where do they cross the y-axis? So whether you mean x-intercepts or y-intercepts, it's the same. Where are the odd power functions decreasing? Are they ever decreasing? And so where are the odd power functions increasing? Everywhere. That seems like a good enough answer. If you happen to prefer negative infinity to infinity, great. If you'd rather indicate it with blackboard bold R, great. Nice. Folks feel pretty good about that? Even root functions. Are the even root functions even or odd or neither or both? So there's the thing to think of. Is that function even or odd or neither? Folks for even? Folks for odd? Folks for neither? Folks for both? Cool. So I think the only votes are for even or neither. So let's test whether it's even by seeing what happens when you reflect it over the x-axis. So take a point on the graph of this, reflect it over the x-axis. Is this new point on the graph of the function? Nope. So is it even? No, it doesn't even have the correct domain to be even. An even function has to have symmetric domain. I guess same with odd. So it is neither even nor odd. Tell me about its intercepts. Where does that graph touch the x-axis or y-axis? Yeah, just say it louder now. Yeah, you are here. Right. There's the x-intercept, which happens to be the same as the y-intercept. Where is this function decreasing? Is it ever decreasing? Well, on its whole domain, it's going up, so never. And I'll say something intuitive that won't quite be correct. So does that mean that this thing is increasing? I'll say the wrong thing first. Everywhere? Is that correct? No, why not? Yeah.
Because the domain is not all real numbers.
Domain isn't all real numbers. It can't be increasing in a place where you can't compute it. So where is this thing actually increasing? I guess it's its whole domain. By looking at this graph, you compute the domain? Yeah. 0 to infinity. Including 0. Nice. Folks feel pretty good? And I guess the one elementary function still on the list on the board is the absolute value function. Let's recall that the absolute value of x is given by x. If x is bigger than 0, negative x if x is less than 0, and 0 if x equals 0. And we've already seen the graph of it a few times. Here's the graph of y equals absolute x. Feel pretty okay? Maybe I'll close. Oh, that's us. This is these same questions. even or odd absolute value function? Or neither or both? If I reflect it over the y-axis, do I get the exact same graph back? Yeah, so that means it is even. Which I guess also makes sense. The absolute value function doesn't care if the input is positive or negative. What is the domain of the absolute value function? What inputs can you plug into it? Negative infinity to infinity, all real numbers. What is the range of the absolute value function? What outputs does it achieve? Right here is 0 to infinity, including or excluding things. Including 0, and you always exclude infinity. Where is the absolute value function increasing? Yeah, and I'll be, on things like exams, I won't be too terribly picky about endpoints, but the definition we wrote down of what increasing means should mean that you have to include the endpoint there. Because even if you start at 0 and you keep going to the right, does the y value keep going up even if you include 0? Yeah, so that's why it should be included. When is it decreasing? Negative infinity to 0, including 0. So notice, like, endpoints tend to be members of both of the intervals of increase and decrease. Not always true if you have, like, a discontinuity of one of these. Groovy. Folks feel pretty good? So here's a pool of elementary functions. If you're ever asked something about the power functions or the root functions, you just know what those graphs look like. Oh, and maybe I'll give the following interacting with computers comment. If you ever want to think about the kth root of x, that will be given by x raised to the 1 over k if you want to interact with the machine while you do these things. Sometimes it's hard to figure out how you're supposed to like input the 4th root of x into a computer. Groovy. Feel pretty good? Nice. And you know what? Let's do. We have access to a computer graphing tool. Let's use it. Let's unpull up these graphs. Square root function. That looks about like what we said the square root function should look like. Cube root function look like we said it should look like. Quark root function look like what we said it should look like? All right, cool. So let's carry on. So the next thing I want to start in on is this idea of transformations of functions. How do you sketch the graph of a function that looks something like that if you know what the graph of f of x looks like? And we'll start with just some of those ingredients today and see where we get. And we'll do computer demos to check this. So let's start with this. So let's suppose you have some graph, you know what it looks like. Maybe it's a graph of y equals x cubed or x of value x or something. How do you get the graph of that same function plus a constant? What should that do to the graph? see, so it's like you're taking all of the outputs and adding a number to them. Outputs are like the y values? What does it mean when you add a number to the y value? Yeah. The graph will move up by whatever that number c is. Shifting graph up by c. And I guess if adding goes up, then subtracting should go down. All right. And so there will be kind of a takeaway of today that somehow when things happen outside of the parentheses, they do exactly what you expect. But inside of the parentheses, something more subtle happens. So what do you think should happen if you take a function and add a constant to all of its inputs? What should that do to the graph? Yeah. It sounded like there was a question at the end, so I'll put the question mark there. It certainly should do something like left or right. It should do something in the x direction. There are people like left there. And people would want right to be there. Well, I think a good way to settle that is let's actually just do some computer experimentation. Give me a function. What function would you like to think about? Is this allowed in Desmos? I think so. Give me a function that has some x's in it somewhere. Yeah. Well, let's make it squared minus 2. There's the graph of the function. I wanted some x's because otherwise, like, some subtlety that I want to demonstrate won't happen. So there is a function. Let's sketch the graph of y. Let's declare a constant. Let's let it run from 0 to 10. All right, so I've just gotten the graph of a new function, f of x plus c, where c is 1. How does the red function differ from the purple function? Yeah. You have to say it though. All right, you pointed. It goes that way. It goes left.
Oh yeah, translates to the left.
Yeah. And if you want something more convincing, Desmos has the fun thing where you can animate, and yeah, it looks like the bigger that constant c is, the more you shift by. Folks feel pretty good? F of x plus c, the graph is given by taking the graph of f of x, shifting left by c. If adding c moves to the left, what do you think subtracting c should do? Exactly the opposite. Move right by c. All right, so let's use this to do some graphing. We know what the graph of y equals x squared looks like. Looks something like that. Let's discuss, what does the graph of x plus 2 squared look like? And we'll track we'll track like summation sets. So how do you go from the graph of x squared to the graph of x plus 2 squared? How should you shift? To the left by 2. So from here to there, you go left by 2. So let's just track some points. I guess this point right here at 0, 0, that'll go to -2, 0. Feel pretty good? Let's just track a few more points. 1, 1. Shift that to the left. You will get -1, 1. -1, 1 will become the point -3, 1. And I think that's enough to sketch a reasonably compelling graph. Let's also check that we get the right y-intercept. Let's do that by locating the y-intercept. How do you find the y-intercept of this function? Yeah. See what happens when x equals 0. So to get the y-intercept, let's plug in x equals 0. You'll get y equals 0 plus 2 squared, also known as 4. So it looks like this graph should go through 0, 4. Is everybody okay? Nice. And let's do the same thing, but plus 2 on the outside. What does the graph of x squared plus 2 look like? Or how do you get it? You shift in what direction? Up by 2. So you'll take this same graph, go up by 2. And we could track some more points if we wanted to, but I don't think I want to. Feel pretty good? Nice. You can put these together and get multiple transformations. Let's suppose you want to take a graph, add 2 to the input, and subtract 2 from the input, and then add 1 to the output. Let's do each of those one at a time. So starting with y equals the square root of x, because that's the function we're starting with here. Well, you know what the graph of that looks like. It does something like this. I want to get the graph of f of x minus 2 plus 1. So I don't know, maybe it would be useful to deal with those two things in 2 different steps, the minus 2 and the plus 1. Which should we do first? Minus 2? Plus 1? Doesn't matter? All right, if it doesn't matter, is have it, but I have to do one of them first, and I think the minus 2 is one of the more popular between the two actual options. Some aspects of order do matter when doing this stuff, but whether you do this or that first does not. All right, so let's deal with the minus 2. So the square root of x minus 2. What does that do to the graph? Right by 2. Nice. Let's do that. So this point here at, 0, 0, we'll go right by 2, wind up here at 2, 0, and then we'll see the same general shape of graph. That seems pretty okay. All right, let's get the plus 1 involved. So go from here to there, right by 2. How do you get the square root of x minus 2 plus 1 from that? What should I do next? Shift up 1? Excellent. So this point 2, 0 will now be the point 2, 1, because it's been shifted up by 1, and then we'll see something approximately square rooty looking. That feel pretty good? And let's check some things using this graph. So whenever you do something using a technique, you should doubt a little bit, and so you should think about how you could check. What seems like a thing one could do to check if this is a reasonable result? There are lots of different answers. What would you want to do?
Plug in 2, 1 and see if it works.
Cool. Plug in x equals 2. That should result in y equals 1. Let's see if it does. So plug in x equals 2. It looks like I get the square root of 2 minus 2. 2 minus 2 plus 1. Is that 1? Nice. That seems like a decent thing. You should be more confident now. Other thoughts for how you might check? Let's suppose you have access to a computer. How could you use a computer to check?
That's most
pull up both of those, have it graphed. If you have access to your handheld calculator, pull up your handheld calculator and have it graphed. Oh, that's still going. Square root of x minus 2 plus 1. That look about in line with what we got? All right, so the computer R says that it checks out. Let's do like one other thing. Let's see if the domain is correct. By looking at the graph, what does it look like the domain is? The domain is like what x values are on the graph? What x values do you see on this? Yeah. 2 to infinity, including or excluding 2. Including 2. Let's also compute the domain from this formula. Let's compute it again. So let's look at that formula. Square root x minus 2 plus 1. I think the only thing I see there that could screw up the domain is the square root. What types of things are you allowed to see inside the square root? Only positive numbers or 0. So that thing inside the square root has to be bigger than or equal to 0. That's by looking at the graph. That's by looking at the formula. Those two check out, and they give the same thing? Yeah. I guess I should write what I actually said. X minus 2 bigger than or equal to 0. But yeah, then you would solve for x. And yeah, those two give the same domain. Cool. Folks pretty happy? Let's close. Yeah, I think here's what I want to do next. So walk with those around you. Start with the graph f of x equal to x. End with the graph f of x equals y equals f of x plus 1 minus 2. So give me that graph. Collaborate with those around you. See if what you get agrees. All right, that feel pretty good? So I guess the graph should look vaguely square rooty. Maybe I'll go on the board because you already had it. So the graph will look something like that. And what's the coordinate of that point that you found on your graph? All right, so I guess that means graph should look something like that. Is my y-intercept and x-intercept reasonable? It looks here like I've drawn it so the y-intercept is positive. Should it be? What is the y-intercept? I didn't ask you to do it already, so we'll take a moment of computation. Yeah. -1. The y-intercept is -1. Yeah, it is. Okay, yeah. I agree. So this point should actually be at 0, -1. Because that means the axis should be bearish instead. So this is a cautionary thing. So when you graph by transformations, you only really track the information you're careful with. If you're not careful to make sure that you have the right intercepts, well, they might be wrong. So you should check at the end when you're done. Neato. That feel pretty good? So the last two transformations that I want to introduce in my 3 minutes left are these two, f of negative x and negative f of x. And let's start with this one first. So negative f of x, that should be like, take a function, but then make all of the outputs negative what they used to be. What does that do to the graph? Yeah. Reflect over the x-axis. It should make all the y values negative what they used to be. Similarly, if you want the graph of f of negative x, you will reflect over the y-axis. Or maybe I'll say this in a second way as well. Make all x coordinates negative. Multiply all y coordinates by -1. Maybe that's a better way to say it. So let's see this in practice. So here's the graph of some function. It happens to be that degree 3 polynomial, but that doesn't matter so much. If that's the graph of y equals f of x, how would you get the graph of y equals negative f of x? Well, I guess it's like a stupid question to ask because the answer is like right above. If you want to get the graph of negative f of x, you reflect over the x-axis. So when you reflect over the x-axis, this point will still be wherever it is, a little bit bigger than 1. These things that go down to that point will go this way. This wiggle up will become a wiggle down. And there's the graph of y equals negative f of x. How do you get the graph of f of negative x then? Do this reflection. Yeah. So, doing that, let's track the points that don't change. This point at 0, 1 will still be at 0, 1. These points that go up and then down will go up and then down just on the other side. Nice. And maybe I'll just close with one thing. These two functions, are they the same function? No, they're similar looking functions, but they're not the same. So tell me, is the original function even or odd or not odd? Not odd. And this check, I guess, tells you it's not odd. If it were odd, these two would be the same. If it were even, those two would be the same. But none of them are the same, so it's neither even nor odd. Neato. So I think here is where something I would like you to do in advance of next time. Go through this example. I don't think it should take long. Go through that example in the notes. We'll discuss it next time, but it'll go better if you've already done. Yeah, you have a good weekend too. Have a good weekend. You too. Thank you. So you might be able to tell by my voice that I'm a little under the weather. I was strongly considering canceling today's office hour because of that. Can you make it to my office any earlier? Can you make it to my office earlier than 1?
Yeah.
Oh,
Okay,
yeah,
cool.
yeah.
I'm at 11. Can you make it to my office at 11?
I'm really confused.
Okay, excellent. Do that. Yeah, I will see you at 11 for that quiz.
Yeah.
Oh, sure. All right.
Can I just take a picture of like my?
Yeah, for like the open-ended hole?
Yes.
Yeah. Yeah. tangent will want you to turn it into a PDF or a JPEG.
I know, right, and I really
And if you have like technological issues it's not letting you, then shoot me an email and attach it to that email and we'll figure something out. Oh yeah. If you would like to learn how to typeset mathematics, we could do that, but that's not one of the goals of the class.
Right, I know, that's why I was like, I don't know how much shape on this. Like, I'm sure because he's actually, yes.
and I looked at him and he was like, sorry, I'm thinking in Spanish. I was like, yeah, sorry, we're doing math right now.
Okay, so this is like a piecewise function you're graphing at the end? Yeah.
No, it goes like that. I know it.
So in order to answer the question, let's think about what the open function is.
Little cutouts is actually.
So you had this point at, was it negative 3 minus 9. That's that one down. Then you had something like that. Okay. I'll not decorate the endpoint at all. And then the other piece is like some positives, like negative. Different from that one. So the graph looks something like that. And let's figure out at that point should that be an open or a solid dot. And to answer that, look at the formula for the function. What is half of negative 3? Did you write down like the whole piecewise definition somewhere? Okay.
Yeah, for that one I know it was like, it was negative 2x plus 6. And then
All right. Is negative 3 less than negative 4?
No.
I don't care about this piece right now.
Okay.
What's the next piece? Is negative 3 less than or equal to negative 3 less than 2? So you would use this formula and get negative 3 plus 6, also known as 9. So that means negative 3, 9 could be on your end. And in fact, it's a formula, so you don't need like a dot at all to do that. Yeah.
I don't know.
Not at all. I think it's supposed to. It's supposed to work directly, I think. There's one objection like that. Just because I like just walk through a thing. Where does that 10 come from? How did you get that 10? Where's that? Oh, just like it's terrible. It just depends, like, the hours. I mean, the world record is. Yeah, so
it's in my head. I have
that was like,
just like looking at this picture, right?
but still.
What do you get when you plug in that equals negative 3? 9. Not that.
Yeah, I just miscounted.
Okay.
And then,
Okay.
so 0, like, it's just a straight line, right?
Yep.
Okay.
I just.
Oh, I'm not.
What was this problem asking you?
Find the distance between six questions.
Okay. Shoot me an email and I'll take a look at it. I don't want to do it right now. Yeah, so that makes me think that it's like a narrow dependent on what you give. And I know that there is a problem coming up that has that. It's not this one, I don't think. That one. It's like a graphic problem. It's trying to graph your answer. But if your answer is too big, too fast, it'll blow it out. So it might be that. But shoot me an email and I'll take a look. Yeah.
Oh, stop recording, please.